Hello there, Cape Chemistry Unit 2 students. Welcome back to another video with us here at LMDN STEM Academy. We will be going through the solutions from the May-June 2023 Cape Chemistry Unit 2 Paper 2, right? So let's get into some solutions here. So question 1 is from Module 1, right? And it's asking us to name a compound, give the IUPAC name for this compound here, compound A, right? So the first thing we're gonna do is label our longest carbon chain. And so when we do that, we count from here. So we get 1, 2, 3, 4, 5. It's 5 carbons long, and so that will form our base name of the compound. So that will be a pentane, right? We know it's an alkane because they're only carbon-carbon single bonds. So it's a pentane, that's our base name, right? And then on the third carbon, you see that we have this bromine atom here. So this is a bromo group. And so we have 3 bromopentane, okay? All right, so moving along to part B now. Part B says that a hydrocarbon with molecular formula C6H14 is known to have 5 structural isomers, right? Remember, structural isomers have the same molecular formula, but they differ in the way that we draw them, okay? So they're asking us now to draw the structures for each of these isomers in the space provided below. So, of course, we know that this is an alkane because when we apply this general formula here, we see that it works out here of CnH2n plus 2. So we know it's an alkane. In fact, it's hexane, right? Because it has 6 carbons and they're all single carbon-carbon single bond. So we have a hexane here. So to begin, we can just draw the most general form of a hexane, which is the N-hexane form, where we have 6 carbons just in a straight line. And of course, we're gonna all add the hydrogens around them to make sure that there are 4 bonds coming from each carbon, okay? So that's what we did for this first case here, just your regular straight chain 6 carbons, okay? So then we can move down here and we make our longest straight chain made up of 5 carbons, and then we can add a methyl group onto one of these carbons. In this case, I chose to add it to the second carbon. So I add the methyl group here. And so if I were to name this, this would be what? 1, 2, 2-methyl pentane, okay? It's the exact same molecular formula, C6H14, but I've drawn it in a different way, where 5 carbons form my base, and then there's a methyl group coming off of it, right? So then moving along to the third isomer, I can still have my long 5 carbon base chain here, but then I'm gonna shift the methyl group to the next carbon, right? So now I have my methyl group on the third carbon. So this is 3-methyl pentane. Again, the formula is still C6H14, but the way I've structured it, it's different, okay? So it has a different compound, right? So now I have this one now where I have my longest chain being made of 4 carbons. And then on one of my carbons, so my second carbon here, I have a methyl group here and a methyl group here. So if I were to name this one, then it would be 2, right? So on my second carbon, I have a methyl group, and also on the second carbon, I have another methyl group. So this is 2,2 dimethyl butane, because my longest chain is made up of 4 carbons, okay? And then I can also have another case where I have my longest chain being made up of 4 carbons, but then I have a methyl group on this second carbon, and then I have another methyl group on this third carbon. So this one would be what? It would be 1, 2, so it would be 2-methyl, and then 3. So it would be dimethyl, because there are 2 methyl groups in all. So it would be 1, 2, 2, 3 dimethyl butane. Okay, so that's my 5th one. And so those are our 5 isomers, right? So we have this one up here, and then this, and this, right? So that's 5 of them, right? So then the next question is asking us to say the IUPAC names of any of the 2 isomers in B. So any of these isomers that we drew up here, I name them as I go along, just to make sure that I don't have any duplicates, right? So we can say we have 2-methyl pentane and 2,3-dimethyl butane. So this is my 2,3-dimethyl butane. and this is my 2-methyl pentane, okay, where my methyl group is on that second carbon here, okay? So that's that. So then now they're asking us to write the IUPAC names of the geometrical isomers B and C shown below, right? So you see that we have an alkene here. So there's a carbon-carbon double bond here. And in this particular case for B, we see that we have these substituents on opposite sides of the carbon-carbon double bond. We have one down here, we have a methyl down here, right? And then, so this is our methyl, and then we have an ethyl up here. They're on opposite sides of the carbon-carbon double bond. And so we can say that that's a trans molecule, right? So let's count our longest chain now. So it's 1, carbon 2, carbon 3, carbon 4, and a carbon 5. So we know that it's an alkene because of the double bond. So it will be what? A pentene. And because the carbon-carbon double bond is on the second carbon, we say pent2ene. And because the substituents are on the opposite sides of the double bond, we say it's a trans molecule, right? That's a geometric configuration. So it's trans pent2ene for B. And in this one, of course, we see that the substituents are on the same side of the carbon-carbon double bond. So they're on the same side. And then in this case, they're on opposite sides, right? And so when they're on the same side as they are in this case, we say it's a cis molecule. And so this one is going to then be cis pent2ene. Same number of carbons as before, 1, 2, 3, 4, 5. So it's the same thing. It's cis, but then pent2ene is the same. But the first part, the prefix is going to be cis because the substituents are on the same side of the carbon-carbon double bond, okay? So that's what was required for us for here, for C part I. So moving along to C part 2. C part 2 says compound B in C part I. So this compound here, this trans pent2ene, is going to react with HBr to yield Markovnikov product D as an equal mixture of 2 optical isomers, right? So now we're getting some optical isomers being formed when this trans molecule reacts with HBr. So then they're asking us now to define the term optical isomer. What is an optical isomer, first of all, before we even get into anything else, is what they're saying, okay? So an optical isomer is a type of isomer that arises when there are 4, right? There are 4 different groups attached to a central carbon atom, 4 different substituents, right? And then now the 2 isomers that are formed, right, are going to be mirror images of each other. So this is how we would define an optical isomer in its complete terms, right? 4 different groups attached to a central carbon. And so the 2 isomers formed are going to be mirror images of each other, okay? Okay, so now for part 3, they're asking us to draw the structures of the 2 optical isomers obtained in C part 2. So in here, when the compound B reacts with HBr to form this Markovnikov product, which are optical isomers, let's draw the structure of those optical isomers, right? That's what they're asking here. So just follow me down here. This is our compound B from up here, right? So that's our trans molecule here. Now, when we add HBr, right, we see that this is an unsymmetrical molecule, right? Because we have this carbon has a hydrogen here, this one has a CH2, CH3 here, this one has a hydrogen here, and this has a methyl group. So this is a methyl group, and this one has an ethyl group on it, right? So now, when we have the HBr, based on Markovnikov's rule, right, the hydrogen is gonna add to the carbon that already has more hydrogens to it, right? And in this case, that's this carbon here. So we have so we look at this one over here. Let's look here. This is our major product right here, and this is our minor product. So we're gonna get 2 products, right? We're gonna get one where the hydrogen adds to the carbon that has the most hydrogens, which is this one. So the hydrogen being added here, this blue hydrogen here. And then, of course, the bromine is going to add here to this one, right? So that's what we have shown here. And then we also have this product, this minor product, where we have the H adding to this carbon and the Br adding to this carbon. But they're asking us about optical isomers. And remember earlier what we said about optical isomers. Optical isomers have a chiral center, meaning they have a carbon that has 4 different groups attached to it. And so if we look at this major and minor product, we see that this is going to be our major product then, because this is a chiral carbon. There's a hydrogen here. There's a methyl group here. There's a bromo group here. And then there's a propyl group over here. So attached to this carbon, there are 4 different groups. So this is a chiral carbon, and this will form an optical isomer, right? It will have a mirror image of it that I've shown down here, right? So this is our major product with that chiral carbon. It's gonna have a mirror image of it, right? In equal amounts, that's what the question told us. And so here we see that we have that where whatever was on the left over here is on the right, and whatever was on the right is on the left, right? It's just a mirror image of it. So you can imagine there being like a mirror here in the middle, right? And it's just flipped. So these are the 2 optical isomers that are gonna form from the addition of HBr to compound B. So this is actually our final answer. This is what they're looking for, right? This equal amount of 2 optical isomers is what they'd asked us for. So this is our final answer. But we got there by adding this HBr across this double bond here, okay? All right. So moving along to part 4. Part 4 says to state the color change observed when compound C in C part 1 reacts with Br2. So what was compound C again? Compound C was this one. And if this compound C reacts with Br2, then we know that the Br is gonna add, right, across this double bond, right? And so we'll end up with something like this. We'll end up with C, single bond C. Then of course the H's are gonna remain, or substituents. CH3 is gonna still be there. We're gonna add the Br here, and we're gonna have the other Br here, and then of course the ethyl group that was there will remain there as well, right? So that would be CH2, CH3 will remain. No, what is the question asking us now? We know that this is gonna be our product. We're gonna go from a carbon-carbon double bond to a carbon-carbon single bond. And so what's gonna happen in terms of a color change, right? We know that bromine, or this bromine water, is generally orange or red-brown in color. When it reacts with an alkene, the alkene is gonna decolorize that bromine. And so we're gonna see that color change from orange or red-brown to colorless, the decolorization of bromine. And so that's what they want here for our 2 marks, okay? All right, and they really want us to say what the color change is, meaning what was it before, right? So what is the color of the bromine solution before, and what is it gonna be when you add it to compound C, and it's gonna go from orange or red-brown to colorless. So be explicit in that, and you get the 2 marks, okay? So moving along to D now, D says, observe the reaction scheme below and answer the questions that follow. So let's look at this reaction scheme. We see that we're starting out with compound A, right, which has this alkene functional group. There's also an OH group here, but boxed in the box is the alkene functional group. So it's a name the functional groups highlighted in the compounds labeled A, B, C in the scheme above. So in compound A, they have highlighted the alkene group, so we write that here. In compound B, they have highlighted the OH group, the hydroxyl group or alcohol group, and so we write that here for B, alcohol or hydroxyl group. Then for C, they've highlighted this carbonyl group here, and this carbonyl group is specific for a ketone, right? So this is a ketone here, and so we said that compound C has the ketone or carbonyl functional group in it, okay? So that's all for 3 marks here. And moving along to part 2, part 2 says to identify the reagents I and II in the scheme above. So what do we need to go from this alkene here to know where we have this disubstituted bromines here, right? So when we're going from a alkene to adding 2 bromine atoms on it, we're gonna need Br2, right? We're gonna need this Br2 aqueous, right? So Br2 in aqueous. So that's the reagent that we need to go from here to here, to go from A to B, right? because the only thing that changed was that we added these bromines across where that double bond was, right? So we need Br2 bromine water or Br2 aqueous for this, okay? And then reagent 2 now, we're going from this bromine is here, and then where the functional group that's reacting is the OH group, the alcohol group. So we're going from an alcohol to a ketone, right? To a ketone here. So this is a secondary alcohol. You see that there's like, there are substituents on both sides of this carbon here. So this is a secondary alcohol. And only when we oxidize a secondary alcohol will we get a ketone. So we need some oxidizing agent here, right? So we can either pick KMNO4, that could work, right? KMNO4 could work here. Or we could use potassium dichromate, right? So K2CR. Right, so we can use potassium dichromate here. And so any one of those will work here. I've just written acidified KMNO4 here. We can also have acidified K2CR2O7. Right, so potassium dichromate would also work there. Okay, so remember now, we're just oxidizing a secondary alcohol to get our ketone. And when we do that, that's what's gonna happen, right? That we're showing there. So moving along now to part 3. Part 3 says identify the color change observed when compound A is converted to compound B. So what was compound A again? Compound A was this alkene here, and we're going to what? Compound B, and we're adding this bromine. So let's see. Okay, so we're going from compound A to compound B, compound A to compound B. So again, of course, we're gonna have that decolorization of this bromine solution, right? The color is gonna go from orange or reddish brown to colorless because we're adding it to a double bond, right? So red, brown, or orange to Br2 is gonna change to colorless. So that's our answer for here, right? So then based on your response in D part 2, what was D part 2 again? D part 2 was here. Based on your response to that, what color is observed for the conversion of compound B to C, right? So in D part 2, we said we're going to use we can use acidified potassium permanganate, or we can use potassium dichromate. If we use the acidified potassium permanganate, and we're going from alcohol to ketone, we're going to have a color change in this. This is going to change from what? Purple to colorless, right? Purple to colorless is what we would see as we go from B to C, right? And then if we were to use potassium dichromate, of course, as our oxidizing agent, we'd go from orange to green, okay? So it just depends on which oxidizing agent you chose, but you're gonna have this color change because these oxidizing agents are getting reduced in the process, and as a result, you see these color changes, okay? So remember now, the oxidizing agent is oxidizing the secondary alcohol to the ketone, but it itself is getting reduced, and it's that causes us to see these color changes, okay? So my answer here, I wrote color change from purple to colorless because the Mn7+ that's in the permanganate is gonna get reduced to Mn2+, okay? So we see a color change from purple to colorless. So this part alone should suffice. What's the color change that you're gonna see? Purple to colorless if we use KMNO4, right? All right. So moving along to part 5. Part 5 says draw the structures of compound D and compound E in the space provided below. So let's see what compound D was gonna be formed from. So compound D is what we're gonna get when we react this ketone with sodium cyanide and HCl, so acidified sodium cyanide, right? And what's gonna happen in that case is that this ketone group, right, is gonna then, it's gonna become a hydroxyl group. So this is gonna become an OH here. And then this double bond is gonna go away, and we're gonna add the cyanide here as well, right? So let's draw what that would look like. So the carbonyl group right, becomes the COH group. Instead, we have this hydroxyl group here and the cyanide being added there. So this is what we would get there. And then for compound E now, we are adding HBr to this compound, which has this functional group here, this carbon double bond functional group. So we're adding the HBr across here, right? And again, when we do that, we're adding it we're following Markovnikov's rule. And so we're gonna add the H to which one? We're gonna add the H where there are already more hydrogens, which would be here. So we're gonna add the H here, and then we're gonna add the Br down here, right? We're gonna add the Br to this carbon here. And so when we draw that structure ends up being this one here, right? Where we add our hydrogen here, we get rid of our carbon-carbon double bond. It's now a carbon-carbon single bond, and the bromine is being added here where there were this methyl substituent, okay? So this is our compound E that's formed from the, by adding a hydrogen halide to this alkene. And then this compound D is formed from us adding in this acidified NaCN, which makes this group a hydroxyl group, and then the CN is added here as well. Okay, that cyanide nucleophile is going to be added in here. Okay, so this is compound D and this is compound E. Okay, so part 6 says name the reaction used to form compound E. So again, we are doing electrophilic addition, right, across this carbon-carbon double bond. We are adding the HBr via electrophilic addition, okay? So that's the mechanism there. That's the reaction used to form compound E, okay? Electrophilic addition. So now moving along to part 7. Part 7 says give the reaction mechanism for each of the steps in going from compound A to compound E using curved arrows to show the movement of electrons, right? Movement of electrons. Now, remember, it is the electrons that are moving. So we're going to always want to draw our arrows, whether they're curved, whether they're half arrows or full arrows, they're going to always be coming from our electrons, right? And so let's look at this now. So we have compound A, which is where we have our carbon-carbon double bond, right? And so this is an electron-rich center, right? So that's where the electrophilic addition comes in. Is that now we have our HBr molecule, right? That's what this step represented. Going from A to E was an electrophilic addition. So we have our HBr molecule, which is a polar molecule. And so this one is going to have a partial positive charge. The H will have a partial positive charge on it. And the bromine will have a partial negative charge on it because it's a polar molecule, right? And so now this electron-rich center, right? This carbon-carbon double bond is going to give one of these double bonds to form a bond with the hydrogen, right? The hydrogen is a partial positive charge. This is electron-rich, so it's negative. And so the hydrogen is going to want to form a bond with it, but we show the arrow coming from the bond where the electrons are to then pull off this hydrogen from this hydrogen bromide, right? And so when that happens now, this bond is going to split heterolytically. So all of these electrons are going to go towards the bromine atom. And so we're going to end up forming a bromide ion. It's going to then be formed as a result of that, right? So let's come over here and see how that hydrogen is going to be attached. It's going to be attached up here, right? Because as we said, it's going to add to the carbon that already had an hydrogen on it, which is this one. So the H is going to add here. We have our bromide ion now that's negatively charged. And so the electrons from this bromide ion is going to come here towards this carbocation that was formed as a result of this double bond going away. So we had a carbocation here that was formed when the hydrogen bonded to this carbon. And so there was a positive center here. And so the negatively charged bromine is going to come in, attach to this positive center here, and then just completely neutralize it. And so in the end, what we'll end up with is the bromine being attached to this carbon here. And of course, the hydrogen was added here. And so that's how we ended up with compound E, right? So let's flip back up and see what we had drawn for compound E. It was this one, right? Where we had the H here and the Br down here. And of course, our OH group didn't change. So you see, This is the electrophilic addition mechanism that we showed here, okay? So all of that for 3 marks and you're good. And with that, that's all that was required of us for question 1, which is the module 1 question, and that's all worth 30 marks, okay? So we're gonna move along now to question 2. Okay, so getting right into question 2. Question 2 says that a solution of potassium manganate 7 is standardized by titration against the primary standard ethane dioic acid, right? The standard solution of potassium manganate 7 is used to determine the percentage of Fe2+ in compound R, okay? List 3 characteristics of ethane dioic acid that make it a suitable primary standard. Now, when we're choosing a primary standard, we want to make sure that what? We want to make sure that that solid ethane dioic acid can be obtained to a very high purity. So if it is that we're using it in this case as our primary standard, then this has to be true, right? So solid ethane dioic acid can be obtained to a very high purity. It is stable in air, so it's not gonna break down, it's not gonna react with air, right? It is readily soluble in water. That's our ethane dioic acid. It's readily soluble in water and it forms a stable solution. So we can then use that as a primary standard to make sure that the solution of potassium manganate 7 has the correct concentration, that we're sure of the concentration of it, so that we can then use it to figure out the percentage of iron 2+ in compound R, okay? So these are the characteristics that make ethane dioic acid particularly useful for that function as a primary standard, okay? All right, so moving along to B now. B says, in preparing the solution of ethane dioic acid for titration against the manganate 7 solution, 2 pieces of laboratory apparatus with high degree of accuracy are required, right? We want high degree of accuracy. Name these 2 pieces of apparatus. So you know, when we're making up these primary standards, or when we're preparing the primary standard solutions, we're gonna need a mass balance, right? So for that mass balance, we're gonna be using that to weigh out the solid ethane dioic acid. And then now we're gonna have to put that in a volumetric flask, right? And then make the solution finally, right, in that flask. And so we need a mass balance to weigh out the mass of the ethane dioic acid that we're gonna use to make that primary standard solution. And then we're gonna be doing that in a volumetric flask, right? So yeah, that's where we're gonna make the solution ultimately. So we need these 2 pieces of apparatus. These are the key pieces that we need when we're making a primary standard solution, okay? All right, so moving along to C now. C says 25.0 cm cubed of aqueous solution of R, that's compound R, that contains our Fe2+, right? That solution requires 24.80 cm cubed of 0.02 mole per dm cube of manganate 7 for complete reaction, okay? So that's when we're doing our actual titration now. We see that the titration, if we titrate at 25.0 cm cube sample of this solution R, that's gonna require 24.80 cm cube of the 0.02 mole per dm cube manganate 7 solution for complete reaction, okay? All right. So the equation for the reaction is as follows. We see that we have 5 moles of iron 2+ reacting with this 1 mole of MnO4-, this manganate 7 ion, plus 8 moles of H+, and that's gonna give us 5 moles of Fe3+, 1 mole of Mn2+, and 4 moles of water. Okay, so this is the balance equation for the reaction, right? So now it's asking, calculate each of the following, the moles of MnO4 minus used. So the first thing I would do, or I suggest students doing these kinds of questions, is first of all, look at your balance equation. You have your balance equation, then you're gonna just zero in on the species that the question is asking you about, right? So the question is asking about this aqueous solution of R, which contains this Fe2 plus. So we're concerned about this species here, and we're concerned about it being titrated with this manganese 7. So we're concerned about this, right? So the first thing I would suggest is just to pull out the molar ratios from these two species that are reacting, okay? And so when we look at this, we see that the molar ratio is what? It's a 5:1, right? So it's a 5:1 molar ratio that the Fe2 plus reacts with the manganese 7. So that's the very first step I would say to do. Even before we jump into any calculations, let's look at the species that are reacting and the molar ratios that they're in, and that's a 5:1. We get that from the balance equation, okay? Okay, so let's look at I again now. I says the number of moles of MnO4 minus U's. We need to calculate that. No. The way that we do that, you see that here they gave us the volume of MnO4 that we used, and they gave us the concentration of the MnO4, right? And we know that moles is equal to what? Concentration times volume, right? So the concentration of the MnO4 minus solution was 0.02 moles per dm cube, and the volume here was 24.80 cm cube. So, we're going to have to convert this to dm cube first of all if we're going to multiply it with this, right? So we have our concentration here, and we're multiplying that by the volume, which we've converted to dm cube. And when we do that, we come out with the number of moles used of MnO4 minus U's as 4.96 times 10 to the negative 4 moles, okay? So we're good for that. That's 1 mark because they literally just want us to apply this formula, concentration times volume, and that gives us our moles of manganese 7, okay? All right. So moving along now to part 2. Part 2 wants us to calculate the number of moles of Fe2 plus that's present in that 25.0 cm cube sample of aqueous R that we used, okay? So how many moles are in that 25 cm cube sample? Again, we go back up here and we look at our mole ratio. We already just calculated how many moles of MnO4 were used. And so this was the 25 cm cube that we used this much moles for. And so because these are in a 5:1 molar ratio, I simply multiply the moles that were used by 5, right? To find out how many moles of Fe2 plus were actually reacted, right? And that's exactly what I did down here. I said 5 moles of Fe2 plus is going to react with 1 mole of this manganese 7 ion. So X moles of Fe2 plus will react with 4.96 times 10 to negative 4 moles. So effectively, I'm just multiplying this number of moles by 5, right? And so when I do that, I come out with a value of 2.48 times 10 to the negative 3 moles as the moles of Fe2 plus that were present in that 25 cm cube of aqueous R, okay? So this is my number of moles of Fe2 plus here. Okay, so remember now, this is the amount that's in 25 cm cubed, right? Now they're asking us about the number of moles of Fe2 plus, then that would be in 1 dm cube. So we kind of have to scale up now, right? This was in 25 cm cube. Now they're asking us about 1 dm cube. So we have to scale up by what? This is 25 cm cube, and we're trying to get to 1 dm cube. So let's convert that 25 cm cube to dm cube. And that's this in this volume. We knew from here that that contains 2.48 times 10 to the negative 3 moles of Fe2 plus. So if we want to find out how much is in 1, then we can do a cross multiplication here where we say, okay, 1 dm cube is going to contain Y moles of Fe2 plus if 25 over 1,000 dm cube contains this much, right? So Y then ends up being equal to 22.4. So this moles up here times this volume here times 1 dm cube divided by 0.025 dm cube. When we do that, we come out with a Y value of 0.0992 moles. So this is the amount that we had in 25 cm cube. This is the amount that we have in 1 dm cube, which is effectively 1,000 cm cube, right? So we could actually look at it this way. If we had 25 cm cube over here, up here, that's what this answer was for, and we're going to 1,000 cm cube, which is the same as 1 dm cube, effectively then we would have multiplied here by 40, right? And so effectively, we're going to have to multiply this number of moles. So we're going to have to multiply that 2.48 times 10 to the negative 3. We have to multiply that by 42, right? Because we're scaling up now, right? Do you see that? That's a little shortcut here. And when we do that, we'd end up with this very same number of 0.0992 moles, right? But your tried and true cross multiplication will always get you there as well. So this is our final answer, okay? 0.0992 moles is the amount of Fe2 plus that we have in 1 dm cube or 1,000 cm cubed of R, okay? All right, so this is a cm cube, right? So moving along to 4 now, part 4 says they want us now to find out the mass of Fe2 plus that's present in 1 dm cubed of R. So in this previous step in 3, we know that there are 0.0992 moles of Fe2 plus in 1 dm cubed, right? So if we're supposed to find out the mass, then in 1 dm cubed, we just have to convert these moles to mass, right? So I said down here, a mole of Fe2 plus has a mass of 56 grams, right? Therefore, 0.0992 moles of Fe2 plus, which is what we have in 1 dm cube, has a mass of Z's are unknown, Z grams, right? So then Z grams now is going to be equal to, again, a little cross multiplication situation where we're going to do 0.0992 moles times 56. And that gives me that there are 5.56 grams of Fe2 plus in 1 dm cube of R, okay? Again, from up here, we knew how many moles were in 1 dm cube. So we're literally just converting this number of moles to mass. And to do that, we just multiply the 0.0992 times the mass of 1 mole of Fe2 plus ion, right? Which is 56 grams per mole. And so when we do that, we come out with 5.56 grams of Fe2 plus in 1 dm cube of R, right? So moving along now, the percentage of Fe2 plus in the compound. So remember now, our compound was actually R, that was the total compound, but a part of that compound is Fe2 plus. So what we've gone through from part 1 down to part 4 is that we found the mass of Fe2 plus that's in that compound R, right? And so if they're giving us a mass concentration of compound R to be 40.90 gram per dm cube, and we know how many grams of Fe2 plus are in 1 dm cube, then we know how many grams of Fe2 plus are in the entire compound, right? And so we can say then that if 5.56 grams of Fe2 plus is in 1 dm cube of R, then 40.90 gram of R and 40.90 gram of R is in that same 1 dm cube, then the percentage of Fe2 plus in that compound will be 5.56 grams over the 40.90 grams, right? And that's going to get us 13.59% of Fe2 plus in that compound, okay? So this is just finding the mass that we calculated as a fraction of what was in the total molecule, and we get 13.59%, okay? All right, so moving along to part D. Part D says a variety of chromatographic methods can be used to separate mixtures. State the meaning of the term retention time as applied to gas liquid chromatography or GLC. So what is a retention time? The retention time refers to the time between the injection and the detection. So the time between when we put the sample, inject the sample, right, into the GLC machine to when we get a detection on that screen is what we call our retention time. So that's for 1 mark, we're good. So now for part 2, it's saying distinguish between a stationary phase and a mobile phase as used in chromatography. So the words themselves kind of give us a clue as to what these two things mean and what's the difference, right? So the stationary phase is usually the solid phase to which components of a mixture are adsorbed to varying degrees. So the stationary phase is not moving, that's the fixed phase, right? And the components that you're trying to separate from in that mixture are gonna be adsorbed to it to different extents, okay? So that's our stationary phase. And the mobile phase is the phase that actually moves over that stationary phase, right? So we have our stationary phase that's fixed, and then we have a mobile phase that's moving over that, and that then allows the separation of the components to occur, right? And the mobile phase is usually a liquid or a gas. So if we capture that, if we capture the fact that one is sticking, that's not moving, and then one is moving, as well as the fact that what their states usually are, so this one is usually solid and this one is usually liquid, then I think we're our gas, and I think we're good for 2 marks here, okay? All right, so moving along to part 3. Part 3 says, give one example of a stationary phase that's commonly used in gas-liquid chromatography. So one example is what they're asking for. So typically, what we're used for a stationary phase in gas-liquid chromatography. So our stationary phase is generally going to be a liquid. So it's going to be a long-chain hydrocarbon oil that has a high boiling point. And they're going to put that on a silica or aluminum support. That's typically how the GLC stationary phase is structured. And so if they want a very specific example, we could say polydimethyl siloxane. This one is called for short PDMS, right? That forms our stationary phase in GLC, or PEG polyethylene glycol. Okay, so these are some commonly used stationary phases in GLC. All right, so now it's saying, give one example of the use of chromatographic methods of separation in industry. So how do we use chromatography in industry? There are a variety of ways. Any way that you put here, they just ask for one. Any one that you put should suffice. So I put like 3 here just for completeness, or just to give you some examples of what could go here. It's used in forensic analysis, so that's chromatography in general is used in forensic analysis to identify and quantify compounds. We actually use GLC to do this. It's used in medicine to determine gas concentration in blood samples or for fuel analysis. We use chromatographic methods of separation to test the urine or the blood of athletes for performance-enhancing drugs. And of course, there are other wide variety that you can think of, right, to separate what? There's so many different things that we use them for in industry. So these are just 3 examples here, right? So 1 mark, just give 1 and you're good. So moving along now to part E. Part E says to define the term retention factor, or the RF value. And the retention factor, or RF, compares the distance moved by each component of the solute to the distance moved by the solvent during paper or thin layer chromatography, right? So that's what the retention factor is. And then now, part 2 says samples of 2 different brands of black ink are separated into their constituent parts using paper chromatography, right? Both samples contain a red dye. Now, in the first sample, the solvent, the distance traveled by the solvent is 7.54 centimeter, while the red dye, which is that component of that ink, right, travels 4.67 centimeter. In the second sample, the red dye travels 3.31 centimeters, while the solvent travels 5.34 centimeters. So now they're asking us to calculate the RF value for the red dye in each of the 2 samples. So remember from up here what we said the RF value was. We said that the RF value of the retention factor is the distance moved by the component of solute over the distance moved by the solvent. So for sample 1, our RF value is going to be distance moved by the component of the solute, which is this red dye. This red dye moved what? 4.67 centimeters in this first sample, and the solvent moved 7.56 centimeters. So when we divide those through, we get 0.619, right? And when we do that for the second sample as well, where the red dye moved 3.31 centimeters and the solvent moved 5.34 centimeters, then we came out with that number again, that very same number of 0.619. So the RF value for both of these dyes are the exact same, okay? So deduce whether the same red dye is used to make both types of ink. Remember, we're looking at 2 different brands of black ink, right? And they're separated into their constituent parts, right? So is it true? Can we say that the same red dye is used to make both types of inks? That's true. And why? since in both samples, the retention factor of the red dye is the same, meaning that the distance moved by the solute over the distance moved by the solvent ended up being the exact same value, that means that the same red dye is used to make both inks, both types of inks, right? And we can deduce that because the RF values are the same, it means that the red ink, they were absorbed to the stationary phase to the same extent. Whether it was in sample 1 or sample 2, they were absorbed to the stationary phase in the same extent. And so when we compare it to the distance moved by the red ink to the solvent, we end up with the same number. And so we know that they're the same red dye in both types of inks, okay? And so if we capture all of that for 2 marks, we're good, okay? So the RF factor is the same, which means that they're absorbed to the stationary phase to the same extent. And so we can deduce then that both brands use the same red ink to make their pens, okay? So moving along now to part F. Part F says, explain the term solvent extraction. So solvent extraction is a method, a separation method that can be used to separate 2 solutes dissolved in a solvent, right? So we have 2 solutes and they're dissolved in the same solvent. And if we want to separate them, we can use solvent extraction. And the way that we would do that is we can use a solvent with which one of the solutes is immiscible. So one of the solutes doesn't mix with it, right? While one of the other solutes mix very well with it, okay? So it's used to extract one of the solutes from the mixture that way. So that's how we do solvent extraction. It's based on the specific solubility of certain solutes in a solvent versus in another one, right? So that's how we can separate these two. So if we capture all of this, we are good for 2 marks. So next they're asking us to state one use of solvent extraction. And we can say that in cosmetic manufacturing, we can use solvent extraction to formulate hair coloring and cosmetic creams, or we could say that we use in the food industry to analyze the solubility of compounds in fats and waters, right? And we can use it for ether extraction in chemistry labs as well. And there are a host of other ways in which we can use solvent extraction. So just pick your favorite way, your favorite use of it, and you'll be good for this 1 mark here, okay? So then for part 3, it's saying describe what is meant by the term partition coefficient as it relates to solvent extraction, right? So partition coefficient refers to the equilibrium constant, which is equal to the concentration of a solute in the organic phase divided by its concentration in the aqueous layer. Because remember earlier when we said, we're using a solvent that only one of the solutes is very soluble in, and we're going to use that to separate the 2 components. So whatever that component is going to have a very specific solubility in the organic solvent that we use, and so it will have a different concentration in the organic phase than in the aqueous phase. So it's kind of partitioned between the organic phase and the aqueous phase. And so when at equilibrium, we measure the concentration of that solute in the organic phase and divide it by the concentration in the aqueous phase. That's our partition coefficient. So this is how we define it, okay? Okay, so moving along to part 4 now. Let's see, part 4. Part 4 says, under certain conditions, the partition coefficient of substance Q between methyl benzene and water is 12, Q being more soluble in methyl benzene than water. So again, this is going right back up to our definition of solvent extraction. We have a substance that's more soluble in methyl benzene in this case, which is our organic layer, and then it's not as soluble in water, which is then going to form our aqueous layer. And they told us that the partition coefficient, so that equilibrium constant, is 12, right? So these are all information that we get from the statement, the problem statement, okay? So now they're saying determine the mass of Q that will be extracted from 200 centimeter cubed of aqueous solution containing 8 grams of Q by shaking it with 50 cm cubed of methyl benzene, okay? So remember what our KD is, our partition coefficient. It's equal to the concentration of Q in the aqueous layer over the concentration of Q in the organic layer over the concentration of Q in the aqueous layer, and that's equal to 12. The question told us that, okay? So moving down now, we know that concentration is the same as mass divided by volume, right? So concentration is mass per unit volume. That's a mass concentration in this case, because they're asking us about masses, right? And they're giving us a mass. So we're gonna use a mass concentration. So the mass of Q in the organic layer over the volume of Q in the organic layer divided by the mass of Q in the aqueous layer over the volume of the aqueous layer is gonna be our KD then. It's the exact same thing, it's just concentration written in terms of the mass and the volume, okay? Since they gave us a volume and they gave us masses, we just simplify it this way, okay? So I said here, let M be the mass of Q in the methyl benzene layer or organic layer. That's what they're asking us to find. The mass of Q that will be extracted from the aqueous layer into then the methyl benzene layer, okay? So I have here that what we ultimately are gonna get in the methyl benzene layer is M, a mass of M, and that's gonna be in what? 50 cm cube of methyl benzene. And then that M is gonna be coming out of the aqueous phase that they told us contain 8 grams of Q at the beginning, right? So in the aqueous layer, we have 8 grams of Q initially, and we're gonna take out M. When we shake it with methyl benzene, M is gonna come out and then go into the organic phase, which is the methyl benzene, right? So in the end, at equilibrium, we're gonna have 8 grams minus the M that left it to go into the organic layer or the methyl benzene. And that's gonna be then divided by the volume of that aqueous layer, which they told us was 200 cm cube, right? So again, we're still consistent. This is a mass concentration in the organic layer, and this is a mass concentration in the aqueous layer. And again, that's going to be equal to our partition coefficient, which they told us is 12. So at this point, all we have to do is just some algebraic expressions that we will then use to solve for M, right? Which is our unknown. So when we come through, cross multiply, bring all the M's to one side, we're going to end up dividing 96 by 16, and then we'll come out with a mass of 6 grams of Q. So that 6 grams of Q is the mass that will be extracted into the methyl benzene layer. So remember, that's what we said our M was. M is the mass of Q that ends up in the methyl benzene layer when we shake it with this solution that has 8 grams of Q in the aqueous layer, okay? So these are our steps, and this is our final answer of 6 grams of Q, okay? So that brings us to the end of question 2, and we're moving along to question 3. So question 3 is our module 3 question. It deals with industry and the environment, okay? So 3 part A is talking about chlorine and saying that chlorine is produced in industry by the diaphragm cell electrolysis of saturated aqueous sodium chloride or brine, okay? So it's saturated, which means that it has a ton of sodium chloride. So a ton of sodium ions and a ton of chloride ions, right? That's what saturated mean. And so for part 1, it's asking us to write half equations to represent the reactions taking place at the anode and what's taking place at the cathode in the diaphragm cell, right? So when we're electrolyzing the sodium chloride, what's going to be happening at the anode and what's going to be happening at the cathode, okay? So to determine that, unless you've memorized these and you just want to jump into writing it, right? We can go from first principles and say, okay, we have sodium chloride. We know that's saturated, so we have lots of this. So let me just write out lots of Na. Na plus Cl is what we have, right? So we have a sodium ion, that's a cation, and we have H plus ion from the ionization of water, right? So the water, because it's aqueous, so the water is going to ionize and give us these, right? And then this is from the NaCl, from the sodium chloride, of course. So we're going to have cations. The cations in that solution are going to be Na plus and H plus, and the anions are going to be Cl minus and OH minus, right? Now, of these cations, only H plus is going to get discharged at the cathode. Remember, cations go towards the cathode, So the H plus is going to get discharged at the cathode because it's lower in the discharge series, right? And then as it relates to the anions, now we know that anions are going to go towards the anode, and only Cl minus is going to get discharged at the anode because we have a lot more of it compared to the OH minus that we have from the ionization of water. So only Cl minus is going to get discharged because it's in a higher concentration than the OH minus ions. So when we come over here now, at our anode, we're going to have that anion, that chloride anion migrating towards the anode. And we know that at the anode, oxidation takes place. So the Cl minus ion is going to get oxidized to chlorine gas, right? And those 2 electrons are what it would have lost, right? So oxidation takes place here. So this is oxidation step at the anode, right? And then at the cathode now, we have reduction, right? And we said at the cathode, we're going to have that H plus cation going towards the cathode. Once it goes there, it's going to get reduced. So it's going to gain 2 electrons, the 2 electrons that the chloride ion actually lost. It's going to gain those 2 electrons, and it's going to then form hydrogen gas, okay? So these are 2 half equations. We write these half equations, we show the state symbols of the species, and we show that the charges are balanced. We are good for 2 marks, okay? So this is what they're looking for the 2 marks. So moving along to part 2, part 2 says deduce one reason why the anode in the diaphragm cell is not made of steel, right? So the anode in the diaphragm cell is actually made of what? Titanium, and then the cathode is made of steel. But they're asking us, why is it that the anode in particular is not made of steel? So we know that steel is an iron alloy, right? And so at the anode, what's actually happening is that what? We have chlorine gas being evolved or being liberated, right? And so what would happen if we were to have steel at the anode is that the chlorine would oxidize the steel anode, right? The chlorine that gets evolved would oxidize the steel anode and cause corrosion of the steel over time. And we don't want that, right? We want our diaphragm cell to last as long as possible. So we don't want the chlorine gas that's being evolved at the anode to oxidize and corrode it. And so we're not going to use steel to make it, okay? So no steel at our anode, we use titanium, okay? So moving along to part 3, part 3 says, in the production of chlorine, as well as the manufacture of chlorine-containing compounds like PVC or chlorofluorocarbons, environmental issues are commonly raised. Discuss 2 environmental concerns associated with each of the following, okay? So the production of chlorine using diaphragm cells, what are some concerns, some environmental concerns that arise from that? Well, you know that asbestos is used to make the diaphragm cell. It's actually what the diaphragm is made of, right? Asbestos. And so that asbestos has to be changed regularly, and this process releases asbestos fibers in the air. And we know that asbestos that's not good for us, right? It can cause lung cancer. So that's one of the concerns about using this diaphragm cell to produce chlorine. And then secondly, sodium hydroxide is also a byproduct of the production of chlorine using diaphragm cells. And that sodium hydroxide can leak into the environment. It can then alter the pH of water. And as a result, it can lead to the death of organisms, okay? So that's an issue there as well. That concerns us regarding the environmental challenges that these chlorine production using a diaphragm cell can cause, okay? So then now they're asking us to discuss 2 environmental concerns associated with the manufacture or use of PVC or CFCs, right? How does it affect the environment? Well, PVC is non-biodegradable and contributes waste to litter and landfill. So we're going to be loading up our landfill with these waste from PVC because we can't break it down. It's not going to break down naturally, and so it's going to fill up our litter and landfills and it contributes to waste. And then if we burn the PVC, it can release poisonous dioxins and hydrogen chloride into the atmosphere. And of course, you know, this is bad for us, right? So we don't want that. So this is if I spoke about PVCs. And of course, if you wrote about chlorofluorocarbons, then you could write about the effect that those have on the ozone layer, right? How that contributes to breaking down of the ozone. That's what chlorofluorocarbons do, right? So you can talk, you'll be able to talk about that from an environmental standpoint, how that affects the environment. But for this example here, I just wrote out about PVC, okay? And how PVC would have affected the environment. So either one that you chose, as long as you wrote out 2 detailed concerns, you would be good for your 2 marks here, okay? So moving along to part B says this tetrachloro, what is this? Tetrachlorocarbon, right? CCl4 is an effective fire extinguisher, is effective in fire extinguishers, but it's no longer used because of its toxicity and its role in the depletion of the ozone layer. In the upper atmosphere, a bond in CCl4 breaks and reactive species are formed, right? So identify the condition that causes a bond in CCl4 to break in the upper atmosphere, and then deduce an equation for the formation of the reactive species. So in the upper atmosphere, we have UV light, right? So what's gonna happen is that when the UV light strikes the CCl4 molecule, it's gonna break one of those CCl bonds. It can do that very easily. So when it breaks one of these CCl bonds, it's gonna break in a homolytic fashion. So this chlorine is gonna, so it's gonna be homolytic, right? So it's a half hook where one goes here and one goes here for one of those bonds. And so we're gonna have a chlorine radical that's being formed. So the condition is that there's homolytic fission by the UV light that's present in the upper atmosphere, and that would be our initiation step, right? If we're thinking about it from a reaction step standpoint. But the condition is that there is the UV light that causes homolytic fission, right? So the equation then is gonna be that we have our CCl4 bond. In the presence of UV light, that's gonna form this chlorine radical, and then the CCl3 radical as well, right? So that's what they expect to see from us here is the radical formation, and these radicals are then gonna be our reactive species. Those are the reactive species that get formed, okay? As a result of that homolytic fission by UV light, we have these radicals forming, okay? So part 2 says the reactive species formed from CCl4 act as catalysts, right, in the decomposition of ozone. Write 2 equations to show how each of these species are acting as catalysts. So again, we have these radicals that form, and the radicals are the reactive species, and they are acting as catalysts. They can catalyze these reactions to break down ozone, which results in the depletion of that ozone layer, right? So they're asking us to write 2 equations to show each of the species. So there are 2 species. This would be species 1 and species 2, right? This is one radical and this is the other radical. So let's show how the first radical, which is just a chlorine radical, is gonna break down ozone. It's gonna react with ozone to form this chlorine oxygen radical and oxygen. So the ozone gets broken down into oxygen, just the diatomic oxygen here. And then this is our other radical, which is a CCl3 radical. That's also gonna react with ozone, break it down, and then we're gonna get some more radicals, a chlorine radical and the CCl2 radical, as well as O2 gas. So we're breaking down ozone in each case by addition of these radicals that are forming in that upper atmosphere, right? So if you wrote these equations, you get your 1 mark. So moving along now to 3. 3 says state the name given to this upper atmosphere. Now this upper atmosphere where we have a ton of UV light that can break these CCl4 molecules up, the region is called the stratosphere, okay? So if you said stratosphere, 1 mark, you're good. So moving along to part 4. Part 4 says discuss the importance of the ozone layer to all life on planet. So what is the importance of the ozone layer? Well, the ozone layer is important for all life on Earth since it absorbs harmful UV radiation from the sun, right? And because the ozone layer does that, it reduces our risk of sunburn and skin cancer, It reduces aging of the skin because we're not as exposed to those UV rays because the ozone layer sucks it up. And so it reduces also the likelihood of people getting cataracts in their eyes, right? So that's good for both, for all plants, all the organisms on planet Earth benefit from the ozone being there because we're not as exposed to the UV rays that as we would have been if the ozone wasn't there. And so that's why we need to preserve the ozone layer, right? Because it shields us from UV radiation and enables us to be free from skin cancer and all these things that we just listed here, okay? So if you captured all of this, why it's important from that standpoint, because it shields us from UV radiation, then you would have gotten your 2 marks, okay? So it's not enough to just say that it shields us from harmful UV rays. You have to give an extension of that. Like, okay, it does that. And because it does that, what does it prevent us from having? Okay? So this second sentence is very important as well for your full 2 marks. Okay? So moving along now to part C. Part C is about the carbon cycle. It says that the carbon cycle describes a process in which carbon atoms continually travel from the atmosphere to Earth and then back into the atmosphere. Figure 1 represents a simplified version of the carbon cycle with some processes labeled A to E. So the figure is labeled A to E. There are some processes that are here and then some other stuff, right? So this is our carbon cycle, simplified version of it. Just take a look at it. And then now they're going to ask us to identify the components labeled A, B, C, D, and E in figure 1. So let's look at A. A shows sunlight, right? Having some conversion and going into these plants, right? So that process would be photosynthesis, where we trap the sunlight and the plants use that, right, to make their food. So this is a photosynthesis step. So that's A. And then B, now we have this cow here. The cow is respiring and giving off carbon dioxide back into the air, right? So that's an animal respiration step in B. And then C, now we have these dead organisms and waste products. It's going to form some fossils and fossil fuels down here, okay? So C represents fossils and fossil fuels being formed as a result of the decay of these dead organisms and waste products. So then let's look at D. D shows a plant respiring and giving back carbon dioxide into the atmosphere. So D is going to then be plant respiration. And then here we see E, we see that there are these roots, and the roots respire too. So the E is going to represent root respiration, okay? So that's our components labeled from A through E. And for 5 marks, if you touched on all of these, you are good for 5 marks, okay? So moving along now to part 2. Part 2 says some Caribbean islands are encouraging citizens to use solar energy to generate electricity for household use. Explain how this initiative will help maintain levels of oxygen and carbon dioxide in the atmosphere. Okay, so here's how we're going to approach this one for 3 marks, right? Solar energy, we're going to use that. They're encouraging us to use that to generate electricity in the Caribbean. What do we currently use? Currently, fossil fuels are the main source of electricity in the Caribbean. So when these fossil fuels are burnt, right, they release carbon dioxide, which is a greenhouse gas, and it's harmful to the environment. We want to minimize that as much as we can. Also, the fossil fuels deplete atmospheric oxygen because when they get combusted, they're actually using atmospheric oxygen to do that. So it kind of throws us off balance, right? That's the current state of affairs. No, if we use solar energy, then we minimize the amount of excess carbon dioxide that goes into the atmosphere, so we can maintain reasonable levels of oxygen in the atmosphere, as well as reasonable levels of carbon dioxide, because we're not putting in any excess from burning fossils, and we're not using up any oxygen to also burn these fossils, okay? So fossils are going to produce the carbon dioxide, which we don't want. We don't want that greenhouse gas, and we also don't want to be using up oxygen. So if we go now more towards a solar energy approach, we're minimizing those things, and so we're able to maintain a healthy level of oxygen and carbon dioxide in the atmosphere. So we say all of that, 3 marks, we're good, okay? So moving on to part D. Part D says define each of the following terms. What do we mean by reuse? Reuse means to use something more than once, right? And we use that thing more than once. We can use it for the same purpose or for a different purpose. What does reduce mean? When we reduce something, it means to decrease the amount of materials used, right? To make that thing, to manufacture that thing. So if we decrease the amount of materials used, then they will result in a reduction in the amount of discarded waste. So if we don't use a lot of materials to make the thing to begin with, it's going to reduce the amount of waste. So that's good, right? Discarded waste. So what does recycle mean? Recycle means to manufacture new products from old ones. So we're going to take an old product and we're going to manufacture a new one from that. So that's what we call recycling, okay? And that's for 3 marks. And moving right along to part 2 now. Part 2 says 2 suspected pollutants present in runoff from a community landfill are lead, so the lead 2+ ion, and nitrates. They suspect that these pollutants are present, right? So complete the table below outlining simple laboratory tests that would confirm the presence of this cation here, this lead 2+ cation, and this nitrate anion. So it's a very qualitative thing now. We're going to do some qualitative tests, some lab tests to test for the presence of Pb2+ and NO3-, right? So when we're testing for lead, one way that we might do this in the lab is that we can add 1 mole per dm cube solution of hydrochloric acid to the runoff sample. So we're going to take a sample of the runoff, bring it in the lab. We're going to add 1 mole per dm cube of HCl to it. And when we do that, we're going to see a white precipitate form, right? And that white precipitate is what? That's PbCl2, right? Solid that's formed. That's a precipitate that's formed. And then we're going to add hot water to this sample. And when we add hot water, we're going to see that the white precipitate redissolves, right? Then now, we're going to add Ki, aqueous potassium iodide to the acidified water. And if we see a bright yellow precipitate form, then we know that our lead is there, right? And that is because we're forming PbI2 solid, right? So that's our yellow precipitate, bright yellow precipitate, and that's a confirmation that we do, in fact, have this ion in our runoff, okay? All right, so to test for nitrates now, what we're gonna do, we're gonna take a sample again of this runoff. We're gonna take a sample, bring it in the lab. We're gonna add aqueous NaOH to the runoff sample. And then we're gonna add this zinc, Zn or Ale powder to it. And we're gonna warm the mixture and we're gonna get ammonia gas evolved, right? And if we get ammonia gas evolved, and that gas that gets evolved turns damp red litmus paper to blue, then we know ammonia is present, right? But this is a test for nitrate ions. Of course, you know that there are other tests as well that you could use. So this is one of them. And if you wrote any of the other ones and wrote down the expected observations, that should be good as well, okay? So let's see, what else do I want to say about this here? Let's see. So yeah, so there are several tests for nitrate, and this is just one of them that I listed. Of course, you know that you could also use concentrated sulfuric acid, add a small piece of copper, and then of course, what you would get in that case, you'd get nitrogen dioxide, like a brown gas would be evolved, and you know that you have nitrate. So that's one other way that you could have approached this. But just be sure that you write out the test in great detail and the observation that you would expect, and you'll be good for these marks here, okay? All right, so with that, we've come to the end of the exam. I hope that this was fairly reasonable for you and that you felt that you could do it all. Again, thank you for watching this video. Please make sure that you like it. Make sure that you comment, that you share it with a friend, and that you subscribe to our channel for more great educational content from us here at LMDN STEM Academy, okay? Thank you for watching.